Hi, this is Mr. Ray. This is the third video on giant greenhouse math mistake, a second look at climate change. In this video, we're going to take a look at the history of climate change. Now, when we look at the history of the Earth's temperature has fluctuated about 20 degrees Kelvin since life has been on this planet. The average temperature at times has been 14 degrees hotter, and at other times it's been 6 degrees colder. There's been 4 major peaks of high temperature and 4 valleys of lower temperature. And I'm going to show you a graph. Okay, here's a graph of the temperature of planet Earth over the history of Earth since life has begun. But what you first notice when you see this graph, this is from the internet. This area right here covers about 500 or is said to cover 500 million years. This area of the graph right here is said to cover 500 million years. The next area is only covering about 100 million years. So this is 500 million years. The next section only 100 million years. This section is only 5 million years. Okay, this section covers about 1 million years. And then the last section on this chart only covers 20,000 years. So what you immediately notice is this is very condensed amount of time, and as you go from left to right, this is all very spread out, and so it gives the illusion that there was some fluctuations in the beginning, and then temperatures have gone down, and now they've jumped up to the present. If we take this same scale, by the way, this is from Glenn Fergus's graph from the internet. If you take the same thing and draw it to scale, suddenly it looks like this. All 4 of the last sections from this peak down to here, if we were to draw this to scale, all 4 of those sections would fit from here to here, and the blue areas are condensed in this little vertical bar. So you go back here, this fluctuation in this area from here to here is, when it's drawn to scale, is this vertical bar right here, and our temperature right now is right there. Now the midline of these temperatures, of all the temperatures, the midline is the black line, and so each of these notches represents 1 degree up and 1 degree down. And so if you look over the history of Earth has for a long time been much higher temperature than we are today. In fact, right now we're coming off probably the lowest temperature we've ever been and bouncing back to about here. And with the blue areas in the Pleistocene, it bounced up and down. That's the Ice Age. It bounced up 3 degrees hotter, 6 degrees colder. But we can see back here it was 14 degrees higher. Here it was 6 degrees colder. Now it's bounced back here, and it was bouncing back, and now we're here at this point. But even during the Ice Age, we were 3 degrees hotter at times. We were 6 degrees colder at times. Here's the 2 graphs put together. You can see it. All of this part of Glenn Fergus's graph up to this point goes from here to here when drawn to scale. This part, this drop, fluctuation, the drop is from here to here, and this fluctuation that's spread out here is actually the vertical blue bar. Yeah, you can see. The last major high temperature was in the Eocene epoch, when Earth's average temperature was 14 degrees hotter than it is today. Back then, Earth is believed to have been covered with lush forests and plenty of rainfall from pole to pole. Germany is said to have been a tropical rainforest. Subtropical floating ferns grew in the Arctic Ocean area, okay? And even Antarctica was ice-free. So our next question is, how did we go from this Eocene high, 14 degrees higher than we are today? How did we go from this Eocene high down to this low and into the Ice Age? What caused that dramatic drop from which we've bounced back up? And then these fluctuations, what caused the drop from here, from the Eocene high down to the Ice Age? Well, there was a study done by Hans Egger and Ewald Bruckel, called Gigantic Volcanic Eruptions and Climate Change in the Early Eocene. And what they found was there was massive volcanic activity starting in the Eocene, filtered the sunlight and drove the temperatures down. The North Atlantic was splitting open at the time, and it created a great divide of water between Greenland and Scandinavia. One of the largest igneous provinces on Earth was forming. It was called the North Atlantic Igneous Province. When we look at the geologic record of the North Atlantic Igneous Province, we see a transformation from massive liquid lava flows in the form of flood basalts and injections to pyroclastic ash eruptions. Okay, so there's a changeover. You've got hot liquid stuff coming out, creating the heat, and then you've got the eruptions that blow ash into the air. Now, to look at this on a modern scale, the largest known modern eruption was Tambora in 1815. That caused a year without summer and several years of colder temperatures. Tambora's eruption blew about 150 kilometers of ash into the atmosphere. The eruption, another volcano in Iceland in 1783 called Laki, only blew about 1 cubic kilometer of ash, or about 90.91, so almost 1 cubic kilometer of ash, caused 3 years of cooling in the northern hemisphere. So 150 cubic kilometers of ash, several years of colder temperatures, and a year without a summer. 1 cubic kilometer of ash, about 3 years of cooling in the northern hemisphere. The Eocene eruptions, the ones in the North Atlantic Igneous Province, were massive compared to those. About 200 ash layers were deposited. The smallest layers were 6 cubic kilometers of ash, so 6 times what caused 3 years of cooling. 6 cubic kilometers of ash were the small eruptions. Over 200 ash layers were deposited. The largest Eocene eruption was 1,200 cubic kilometers of ash. All right, so 150 cubic kilometers of ash. This was about 8 times the size in cubic kilometers of ash. So the largest Eocene eruption deposited 1,200 cubic kilometers of ash. That's 8 times the size of Tambora. 2 other eruptions measured 500 cubic kilometers each. It's estimated that hundreds of additional eruptions with less than 6 cubic kilometers of ash also occurred, and those were not large enough to deposit an individual ash layer. Large eruptions drove the temperatures down from the Eocene into the Pleistocene ice ages. Now, during the Pleistocene, there were intermittent large eruptions, which caused temperatures to fluctuate from 3 degrees hotter to 6 degrees colder than today. One such eruption in the Ice Age was the Long Valley Caldera in California. It was a 600 cubic kilometer ash eruption. So 600 cubic kilometer ash eruption is 4 times the size of Tambora. So you can imagine these volcanic eruptions. When the volcanoes erupt, puts ash up into the atmosphere. The ash can settle out fairly quickly, but then you've got aerosols going up into the atmosphere like sulfur dioxide that can block sunlight for years. And if you can imagine the amount of volcanic activity that was happening, we have one volcano going off, causing 3 years causes a year without a summer. But if we have a whole province of volcanic activity going on, where you've got the North Atlantic rupturing, and you've got this ongoing volcanism with huge eruptions, much bigger than the ones that we've experienced in modern times, or in recorded history, or modern recorded history, much larger than that. And we have this ongoing igneous province developing. You can imagine how that would suppress Earth's temperatures. So the high that's 14 degrees hotter than today in the Eocene, driven down into the Ice Age by this ongoing volcanism that created the rift in the North Atlantic. Kind of focusing in on the part of the chart that shows this, you've got the Eocene high here Then you've got the volcanism that creates the North Atlantic igneous province, drives the temperatures down into the Ice Age. And then during the Ice Age, we're fluctuating in temperatures. Each time there's a major eruption, it drops the temperature down. When the sky's clear and the aerosols clear up, the temperatures rise back up. So we've been going in the up and down ever since the Ice Age. We've been going in up or down fluctuations, 6 degrees colder than today. And when the sky's clear, we rise about 3 degrees higher than today. And then it drops it down again with some volcanic, what I'm going to call volcanic hyperactivity. So volcanic hyperactivity drives the temperature down. From this, it was massive volcanic hyperactivity that created the North Atlantic igneous province. That's layers and layers of volcanic deposits. Drove the thing down from 14 degrees hotter. Then during the Ice Age, you have fluctuations. The temperature tries to rise up. Hyperactivity or volcanic hyperactivity kicks in, drives the temperatures back down. We've on our recent temperatures are after a bounce back. One was driven down, now we're back up to here. Now I apologize for the quality of this video. I'm not skilled at making videos. I'm just trying to get the word out the best way that I know how. Now, during the Eocene, during the drop in temperature from the Eocene, as the volcanism, the volcanic hyperactivity kicked in, temperature was driven down from the Eocene high down to the Pleistocene low. There was a point here where the carbon dioxide dropped from 760 parts per million down to 600 parts per million. And scientists who believe that in the power of greenhouse gases contend that the carbon dioxide levels dropping from 700 to 600 is what started to build up ice on Antarctica. Remember, in the Eocene, Antarctica apparently had no ice on it. It was ice free from pole to pole. We had subtropical ferns deposited in the Arctic Ocean. And so you had much warmer temperatures globally. But as the carbon dioxide levels apparently in the deposits apparently dropped from 760 to 600 parts per million, you get the snow starting to build up on Antarctica. Well, today's carbon dioxide levels are much lower. Today we're at 405 parts per million. Now, if the drop down to 600 parts per million caused snow and ice to build up on Antarctica, how can 405 parts per million be causing it to melt? And so this is a major evidence against the idea that carbon dioxide levels do fluctuate with temperature, but they don't cause the melting, because if they did, at 600 parts per million, ice and snow was building up on Antarctica, and now we're worried that it's melting at 405 parts per million. So it doesn't make sense. If 600 parts per million caused Antarctica's ice to build up, 405 parts per million is not going to cause it to melt. What was it then? It's volcanic activity. Volcanic hyperactivity drove the temperatures from the Eocene down into the Ice Age. As the oceans cooled, they absorbed carbon dioxide. Colder water can absorb more carbon dioxide out of the atmosphere. So as the volcanism is blocking the sunlight and causing the temperatures to drop, the carbon dioxide is getting absorbed by the ocean. The colder the ocean gets, the more carbon dioxide it takes out of the atmosphere. And so carbon dioxide levels are dropping not to cause the cold, but as a result of the cold. So carbon dioxide is along for the ride. It's not the driver of the climate. The driver of the climate is the volcanic hyperactivity that drove us right down into the Ice Age and then maintained the Ice Age. The Ice Age fluctuated. We know at times it was 3 degrees hotter than today. At times it was 6 degrees lower. But the fluctuations were caused by, again, volcanic hyperactivity. Major activity driving the whole thing down, and then continued bursts, if you will, of hyperactivity that make those temperatures fluctuate. Now, if the volcanism, the hyperactivity settles down, the skies begin to clear, more sunlight comes in, and these temperatures rise back up. Okay, and as they rise back up, the oceans get warmer, they release carbon dioxide, and the carbon dioxide levels go up. So there is a pattern of carbon dioxide going down when it's colder and going up when it's warmer. But it's caused by the oceans absorbing it as it gets colder and releasing it as it gets warmer. Now, today's carbon dioxide levels are because we've added carbon dioxide to the atmosphere. But that's not what's causing the warming. Again, 405 parts per million can't be causing the ice to melt if 600 parts per million caused it to build up. Okay, so our carbon dioxide is not what's driving the climate. What else can we say about the Ice Age? Now, we know that glaciers, ice caps, and cold, deep ocean water was produced by the Ice Age. Okay? So the Ice Age is what produced the ice caps. As that temperature was driven down, ice starts building up on Antarctica. The second thing that the Ice Age brought us was massive glaciers. And the third thing is cold, deep ocean water. All brought on by the Ice Age. What caused the Ice Age was volcanic hyperactivity. Without sustained volcanic hyperactivity, the Ice Age is ending. Okay, the Ice Age ended. Without the ash and the sulfur dioxide to filter the sunlight, the oceans begin to warm up. The glaciers and the ice caps begin to melt back. Carbon dioxide levels are going to continue to rise as the ocean continues to warm. Carbon dioxide levels are going to continue to rise, and we're adding to it. That's not what's causing the warming. What's causing the warming is a lack of volcanic hyperactivity, the same volcanic hyperactivity that brought us the Ice Age. We may be returning to conditions before the Ice Age, when Earth didn't naturally have glaciers, ice caps, or cold, deep ocean waters. It may be that the ice caps and glaciers will continue to melt and the oceans will continue to warm. Well, is there anything that we can do about it? Well, the first thing that we need to realize is that greenhouse gases did not produce the Ice Age. A lack of greenhouse gases didn't produce the Ice Age. The Ice Age produced a lack of greenhouse gases. What produced the Ice Age was volcanic hyperactivity. So if greenhouse gases didn't produce the warming, taking steps to reduce emissions isn't going to do anything for us. Okay, it's absolutely going to fail to make a difference. The temperature equilibrium, once the Ice Age is over and the Earth begins to warm up, we should be reaching an equilibrium at some point. Where is that equilibrium? It could be 14 degrees higher like it was in the Eocene. It could be 3 degrees higher like it was at times in the Ice Age. Or we could be near the equilibrium today, but I suspect, just looking at the graph, since we've been a lot higher in the past and only a bit higher, we're kind of lower than average right now, but we've only been 6 degrees lower than we are today. 3 degrees higher during the Ice Age when the skies cleared. We may return to 3 degrees higher, or we may return to 14 degrees higher when the Earth reaches equilibrium. Well, is there any way is there anything we can do about this? There's also another point. Each time there's a magnetic reversal, the Earth's atmosphere loses some atmosphere. So how many magnetic reversals have there been since the Eocene? If there's been a lot of magnetic reversals since the Eocene, then we may have lost a lot of atmosphere. And if you remember from our other videos, air pressure is a big part of surface temperature. And so if we lose lose atmosphere during magnetic fluctuations, the The atmosphere is not protected, and the solar wind blows away some of the atmosphere. So if we've lost a lot of atmosphere since the Eocene, then we have less pressure. If we have less surface pressure, then we're going to automatically have lower temperatures. And so 3 degrees higher might be the real equilibrium now. We may never reach 14 degrees higher. That may just have been hotter because we had more atmosphere at that point. Now we have a little bit less atmosphere, so we have less potential for high surface temperatures. But what could be done? Is there anything that can be done about global warming, or to help stop global warming, or to help slow it down? The most powerful natural mechanism besides volcanic hyperactivity for cooling the Earth is evaporation. And so, is there a way to take evaporation and use it to help keep the Earth cooler? Well, if you think about it, 1/3 of the Earth's land areas are desert, where you don't get much evaporation. In those desert areas, there are massive empty dry lake beds left over from where they used to have lakes during the Ice Age and immediately after the Ice Age. What if we took wind and solar power and distilled ocean water into fresh water and piped it out to those desert areas? If we could restore places like the Aral Sea, if we could restore massive dry lake beds like the Mongolian deserts, if we could restore some of those massive desert dry lake beds and fill them up, like even Death Valley. Death Valley is a dry lake bed. If we could fill those up with water, we could increase the evaporation, and we could increase the amount of. If we can increase the amount of evaporation that's going on, we can help cool the Earth. We could also irrigate some of the desert areas. Now we wouldn't want to completely wipe out all the desert areas because of the unique life that's there. We'd want to have some preserves for that unique desert life. But in general, if we could irrigate the deserts, and if we could take those dry lake beds and create lakes there, we would be taking a very hot area, or an area where there's very little evaporation, create much more evaporation. The plants would increase evaporation through their leaves. The lake beds or the lakes would increase evaporation from their surfaces. Remember that evaporation is 192 degrees of continual cooling. If we can increase that to another 1/3 of the Earth's land areas and cause them to have abundant evaporation as well, we could possibly head off global warming that way. Okay, at this point I want to switch gears a little bit and talk about the moon and some other planets. Now, the moon is a great illustration of what we talked about in the first video, the giant greenhouse math mistake. The Earth gets about the same sunlight as Earth, which is about 1361 watts per square meter. If you look at the NASA moon fact sheet, it's got an albedo. The moon has an albedo of 0.11, so 89% of the sunlight is absorbed. Now, if we use average radiation, which I explained in the first video, is the wrong way to do it. But if we used average radiation to find the black body temperature of the moon, it would be calculated to be about 277 Kelvin. If you take the whole surface of the moon point by point and calculate the black body temperature for each point on the moon, including the dark side, the average black body temperature of the moon, the real average black body temperature of the moon, is only 155 Kelvin. So you've got 277 Kelvin with the average radiation method, which I demonstrated in the first video how that's the wrong way to do it. Okay, and then you've got the right way to do it, much lower temperature, 155 Kelvin. Well, the moon has no atmosphere. So which one of these is closer to reality? The moon is a little bit closer than Earth is. Earth's got an atmosphere. The moon's got no atmosphere, and so it's a little closer to being a real black body. Well, the average lunar surface temperature is only about 191 Kelvin. 191 Kelvin. the average temperature at the moon's equator, the hottest part of the moon, the average temperature at the moon's equator is only 230 Kelvin. So this is the average of the whole moon, 191. The average at the equator is only 230 Kelvin. Okay, so if this was the correct way to calculate black body temperature, we would expect the moon's temperature to be a little bit higher than this on average. Okay, instead it's lower than this, and this black body temperature is higher than even the moon's the average temperature at the moon's equator. This leaves scientists trying to explain why the moon is so cold. One suggestion is that the nighttime, the long night, makes the average much colder. But I'm going to show you a graph of this. All right, here's a graph of the lunar temperatures that I kind of transposed from the diviner graphs, from the diviner measurements. And so these are daytime temperatures. This is the highest one, the highest line here is the temperatures at the moon's equator. Okay, during the daytime it rises up, and then at night it drops off. And then for the most part of the night, there's a gradual drop in temperature, a very gradual drop in temperature. So you've got a sharp rise in the morning, high temperatures at noon, a little after noon. Then the temperature starts dropping, and then as the night begins, it finishes dropping, and then it kind of bottoms out here and goes into what we in hydrology would call a base flow. But we have a very gradual decline in temperature. So what they're saying is, well, the moon spins slower than the Earth, and so there's a much longer night. Well, you can see that for most of the night, there's not much drop in temperature at all. Okay, so that's kind of a bogus argument. In fact, 98% of the energy absorbed in the daytime has already been released in the first 18% of the night. So there's a rapid drop in temperature at the very beginning of the night, and then you see that, what I just showed you, that very gradual loss of temperature for the rest of the night. Speeding up the moon's rotation is not going to raise the average temperature at all, because temperature is dependent on watts, and the incoming absorbed watts is not going to change. The incoming absorbed watts is what sets the surface temperature, okay, and the amount that is absorbed by the moon isn't going to change. So the watts that impact the surface and the fact that the moon has a 0.11 albedo, those two things aren't going to change. So the high temperatures on the moon aren't going to get above those temperatures, those black body temperatures that we would calculate. So the temperature is not going to go up if you speed up the moon's rotation. The moon also, when you study the temperatures on the moon conducts about 2 to 3% of the energy it receives into the regolith. So those temperatures that we saw, the peaks of them, the top line was the equator, and then these were other latitudes, and I think we got down about 89 was the lowest one. But these peaks are not quite as high as we would expect from the black body temperature, and the reason is because about 2% of the energy, or 2 to 3% of the energy, doesn't go into making the surface hot. It's conducted by contact, that's transferred by contact into the regolith below. If you change the rotation speed, the only thing that you change is that you'll have less heat stored in the regolith during the day to be released at night. So in other words, it's going to affect less kilograms. It's going to heat less kilograms of regolith. So the temperatures in the daytime are going to be the same, okay, but the amount of regolith that's heated below is going to be less if you sped up the moon. So what's that going to do? That's going to create a colder temperature, if anything. So the moon isn't going to be hotter by speeding it up. It could be colder by speeding it up. The reason that the moon's temperature is 100 91, by the way, and not closer to 155, is because of that, what's happening there. That 2 to 3% is being heated, heats the regolith below the surface. So not just the surface is getting that temperature, but the soil below the surface is being warmed a little bit during the daytime. So the moon's warming that soil during the daytime, and the temperature isn't going to get above the black body temperature here. So it's warming that soil, and then at night, the very surface temperature cools quickly. That's that fast drop in the beginning of the night. And then the regolith cools slowly. That's the slow cooling for the rest of the night, for the remainder of the night. And the fact that that energy is stored in the regolith and then released slowly at night raises the nighttime temperature to about 90 Kelvin. The black body nighttime temperature would be 0 because it's not receiving any radiation from the sun. And so the fact that we've got 90 degrees hotter at night than the black body temperature is because of the energy that's stored in the regolith during the day and then released slowly at night. That raises the average temperature. That average temperature then would be 191, whereas the black body temperature would be colder than that, because the black body temperature would have 0 at night, close to these same temperatures during the day, but 0 at night. And so that elevated temperature at night is what causes the moon's temperature to be higher than the real point-by-point black body temperature. Explaining, but if you take average radiation, which is the wrong way to do it, you've got to explain somehow how this temperature is lower than the black body temperature, even though the nighttime is higher than the black body temperature. And if you were to speed the moon up, there would be less energy stored in the regolith to be released at night. There'd be less time it's released. And so you would probably get nearly the same temperatures, because temperatures are based on watts. The amount stored is the joules that's stored and then released slowly at night. The reason why the moon is colder than this temperature is because this is a bad calculation. This is using average radiation, which we demonstrate in the first video. You can't use average radiation to make an average black body surface temperature. And so this is really a meaningless temperature. If we get rid of this, then the moon's condition completely falls into place. We know why this is the black body temperature. We know why the average temperature is a little warmer. It's because some of the energy that's received from the sun warms the regolith, and that makes the regolith releases its heat slowly at night, and so it's got a temperature above 0 on the dark side. So if we take some of the evidence in these videos and apply it to other planets, the conditions on those planets with atmospheres starts to make sense. For instance, the planet Venus. If you take the average radiation for Venus, which is the wrong way to do it, then the black body temperature comes out to 227 Kelvin, done the wrong way with the average radiation. But if you do a point-by-point black body temperature for Venus, it's only 131 Kelvin. Very low temperature. There's not a lot of radiation that reaches the surface of Venus, or that's absorbed by Venus. A lot of the energy is reflected by Venus. There's not that much that's absorbed, so there should be a low temperature black body. What happens on Venus is you've got a very thick atmosphere, and the gravity is close to Earth's gravity. It's a little bit less, but the gravity is squeezing the atmosphere. If you remember from the video, when gases are squeezed, the temperature rises. So the gravitational temperature setting for the surface of Venus is 1028 Kelvin. That is the temperature that we would expect from gravity compressing a huge atmosphere on Venus, that many times more atmosphere on Venus than on Earth. That very heavy atmosphere being squeezed down should produce a surface temperature of 1028 Kelvin. The actual surface temperature of Venus is only 735 Kelvin. Venus does not have a water cycle. It's very dry. So what's cooling it? What is, on Earth, we saw that our gravitational temperature should be in the 500s and the real temperatures in the 200s, but we accounted for that by the water cycle cooling the surface. So what's cooling the surface of Venus? Well, the surface itself is not being cooled, but there's a layer above the surface where you have the sulfuric acid cycle. And just like our water cycle, the sulfuric acid is evaporated as it comes down into the hotter lower atmosphere. It's evaporated, so it absorbs energy here, and then as it rises up, it condenses, forming the clouds of Venus here. So you've got haze, you've got a hazy layer, and you've got a cloudy layer up here. So you've got a cloud layer and a haze layer, where it's evaporation. So you've got evaporation occurring here, you've got condensation occurring up. And so that heat is transferred from the lower area to the upper area, and everything else below cools in an adiabatic pattern. So the cooling is actually occurring here and affecting everything below it to be in line with the pressure starting at this temperature. So the cooling is actually happening above Venus's surface, not at the surface, but it results in a cooler surface. So this is what we expect the surface temperature to be based on pressure produced by Venus's gravity and the mass of its atmosphere. This is what the temperature actually is, and it can be explained by the sulfuric acid cycle cooling the layer above the surface, resulting in a cooler layer below where the cooling is occurring. Cooling is, this area is being cooled, the heat's being transported up, and as a result, from this point down to the surface, there's an adiabatic cooling or pressure-based temperature increase, but it's colder than this because of the cooling that's going on here. This, in other words, this area is being cooled, and that's causing the area below it to be colder than we would expect just from gravity and pressure. So that's the explanation for Venus. Mars. How do we explain Mars? Mars, again, if we apply what we've learned, if you do average radiation to find the black body temperature of Mars, you'd find it's 210 Kelvin. And this is the wrong way to do it by average radiation. So this is too high. The point-by-point black body temperature for Mars is only 121 Kelvin. Okay, so it's much lower. So this is a faulty black body temperature for Mars based on average radiation. This is the point-by-point black body temperature for Mars, 121 Kelvin. Now, Mars has a thin atmosphere. The gravity and the squeezing of Mars's atmosphere, Mars doesn't have as much gravity and it doesn't have as much atmosphere. So the temperature that we would expect from pressure on the surface of Mars is 342 Kelvin. Okay, we would expect, with the amount of atmosphere that Mars has, the pressure and the gravity, the temperature at the surface of Mars should be 342 Kelvin. The average temperature is actually only about 214 Kelvin. What's cooling the surface of Mars? Instead of 342, it's 214. Well, Mars doesn't have a sulfuric acid cycle, and it doesn't have a water cycle to speak of. There's a little bit of clouds that form above Mars, but mostly it's dust being carried by the atmosphere. So if you have dust storms and you have dust that's picked up, dust is heated at the surface. If it's then transported by wind up higher, the dust will release its energy up here and cool, and then it'll fall back to the surface. And so it's most likely the dust cycle that is causing the surface of Mars not to be this hot, but to be this hot. And remember, Mars's atmosphere is almost 100% carbon dioxide. You would expect, if it's got a black body, the average, if you do average radiation, you get the wrong black body temperature, but it's 210. With 100% carbon dioxide, shouldn't it be much higher than 214? Okay, but with gravitational pressure, we would expect it to be higher than that, except for the dust cooling, except for the cooling cycle of dust. That's likely responsible for the average temperature at the surface of 214. Remember, that's much warmer than the real point-by-point black body temperature is 121. And we would expect that. We expect the surface temperature to be higher than the black body temperature because Mars has an atmosphere. And the atmosphere acts like a blanket so that the surface warms the atmosphere by contact and convection. And so you have a warmer boundary of gas between the surface, which is being heated by the sun, and outer space. So at least you have this boundary of atmosphere in between the surface and space that is warmed by the surface, by contact with the surface, and then releases its heat out into space. So there's a flow of energy comes from the sun to the surface, heating the surface. Then the surface in turn heats the atmosphere by contact, and also by some of the radiation is absorbed by the CO2. And then the atmosphere releases that into space. And so having that blanket of atmosphere that's warmed by the ground, warmed by the ground as a layer, as a blanket of insulation between the ground and space, helps raise the surface temperature. So wherever a planet has an atmosphere, it should have the temperature should be higher than the black body temperature, and also lower than the pressure temperature due to whatever mechanism is cooling it. On Mars, that appears to be dust storms. What about Titan? Titan is a moon, okay, but it's a moon with an atmosphere in the outer planets. If you do average radiation for Titan, you come up with a wrong black body temperature of 85 Kelvin. The point-by-point black body temperature for Titan's surface is only about 50 Kelvin. Now, Titan has a little bit more pressure than Earth does in its atmosphere, and so the gravity and the mass put together, we would expect Titan's surface temperature to be about 240 Kelvin. Okay? So the correct point-by-point black body is 50 Kelvin. With the amount of atmosphere that Titan has and the pressure of that atmosphere on the surface, we'd expect it to be about 240 Kelvin. But the average surface temperature on Titan is only about 93 Kelvin. So instead of being 240 Kelvin, it's only about 93 Kelvin. What is cooling Titan? What is cooling Titan? Okay? Well, some energy is being intercepted in Titan's upper atmosphere. Just like some of the, we have about 3 degrees of temperature that would otherwise heat the surface being absorbed by our ozone layer. Well, Titan has some of the energy is being intercepted in Titan's upper atmosphere. It creates complex hydrocarbons in the upper atmosphere. So it's analogous to what's happening in our upper atmosphere when ozone intercepts us. Titan has a second thing that's cooling it, and that's a liquid methane cycle. We have a water cycle. They've got liquid methane. So the methane is evaporated at the surface, cooling the surface, then it condenses, forming clouds, and then it actually rains. They've got lakes and rivers of liquid methane. And so they have we have a water cycle, they've got a liquid methane cycle. And so the temperature doesn't reach what we would expect from pressure alone. All right, but we've got this constant cooling going on that makes the surface temperature 93 Kelvin. Now I'd like to go back over some of the conclusions from all three climate change videos. First of all, carbon dioxide follows climate change. It cannot and does not drive climate change. If a drop from 760 to 600 parts per million of carbon dioxide caused ice to build up on Antarctica, today's level of 450 is not going to cause it to melt. If 600 causes snow to build up, 450 isn't going to cause it to melt. So carbon dioxide is not the driver of climate change. The driver of climate change is volcanic hyperactivity. When volcanic hyperactivity kicks in, it drives the temperatures down because sulfur dioxide blocks the Earth's atmosphere and cooling results. Volcanic hyperactivity is what drove us from the Eocene down into the Ice Age, and volcanic hyperactivity is what kept us in the Ice Age. Intermittent volcanic hyperactivity made the Earth's temperature fluctuate. The Earth's temperature fluctuated from 3 degrees hotter to 6 degrees colder than it is today. And as the volcanic hyperactivity stopped or settled down, so that the skies cleared, and that allowed the temperature to rise back up. So the real driver of climate change is volcanic hyperactivity. Glaciers, ice caps, and cold, deep ocean waters are leftovers from the Ice Age, and they were produced by the Ice Age. If Earth is returning to a higher equilibrium, then they will continue to melt and the temperature in the oceans will continue to warm. The moon's a good illustration of the difference between faulty black body temperature from trying to get a faulty black body temperature from average radiation versus a correctly derived point-by-point black body temperature. So you can use the moon's situation to show that the point-by-point method is the correct method for deriving a black body temperature of a moon or a planet. The moon is warmer than its current black body temperature because the regolith stores some of the heat during the day. The moon's soil, regolith, stores some of the heat during the day and releases it slowly at night, resulting in a dark side temperature of 90 Kelvin instead of the black body temperature of 0. All planets and moons with atmospheres can be understood by using the correct black body surface temperature and the gravitational pressure temperature setting. That is, the surface temperature we would expect from gravity squeezing the atmosphere. What surface temperature would that produce? And then take a look at, compare that to its actual surface temperature and find out what kind of cooling mechanisms are maintaining a lower temperature than we would expect from gravity squeezing the atmosphere. Because there's a wrong way to compute black body temperature based on average radiation, we know that 34 degrees, when they say that greenhouse gases are warming the Earth's surface 34 degrees, that is fiction. It's based on a faulty black body calculation using average radiation. So what happens is the greenhouse gases absorb certain wavelengths, creating a deficit, but share the energy, and then the energy is released in other wavelengths, so a corresponding surplus is created. Greenhouse gases cause a deficit in certain wavelengths and results in a surplus in other wavelengths, and not a trapping of the energy. All gases in the atmosphere produce back radiation and slow the planet's cooling. Surface temperature is set by energy from the sun and by the air pressure that's caused by gravity. Okay, and also by the cooling mechanisms that are in place. So you have energy from the sun warming the ground, you have air pressure caused by gravity to set a surface temperature, and then you have cooling mechanisms so that it never reaches that temperature. Climate change is driven by volcanic hyperactivity. The climate is likely to continue warming due to a lack of volcanic hyperactivity. So the skies have cleared, and so that the cold ocean that's left over from the Ice Age is probably going to continue to warm until the Earth reaches a new equilibrium. The ice caps and the glaciers that are left over from the Ice Age are probably going to continue to melt. whether we change the carbon dioxide or not, whether we change any greenhouse gases or not. Because remember, the greenhouse gases are just part of the atmosphere, and it's the whole atmosphere that acts as a blanket. The most powerful cooling mechanism on Earth is evaporation. Okay, it's 192 degrees of cooling that's ongoing all the time, maintaining our temperature at an average of 288. Our temperature would be 192 degrees higher if it weren't for ongoing evaporation. So ongoing evaporation is continually cooling the planet 192 degrees. It's the most powerful cooling mechanism that we have, apart from volcanic hyperactivity. So if we can't generate volcanic hyperactivity, the next best thing we can do is increase evaporation. If deserts cover a third of the Earth's land area, that's a lot of evaporation that we could create by watering those deserts, by creating lake beds, filling up the dry lake beds that are in the deserts with water, and also irrigating parts, a large part of the deserts. We want to preserve some of it so that we preserve that unique life forms that are in the desert. But if we could use a lot of that desert to increase evaporation, that's our best. That's the strongest mechanism that we could use to cause global cooling, or to head off global warming. If we try to fight global warming by fighting greenhouse gas emissions, we are going to fail, because greenhouse gases are not warming the planet any more than they did before the industrial age. Remember, from the first video, the same number of carbon dioxide molecules absorb the same amount of radiation from the ground, okay? Whether it's 200 parts per million, 400 parts per million, or 800 parts per million. The same number of carbon dioxide molecules will absorb the same amount of radiation coming from the Earth's surface and share the same amount of heat with the molecules around it, and share the same amount of radiation back to the Earth's surface, whether you have 200 parts per million, 400 parts per million, or 800 parts per million. So decreasing carbon dioxide or increasing carbon dioxide is not going to change how much radiation is absorbed, shared, and returned to the Earth. It's not going to change the amount of energy that's given off at the top of the atmosphere either, because when those wavelengths are absorbed by carbon dioxide and the heat is shared with other molecules, all the molecules, not just carbon dioxide, not just water vapor, all the molecules in the Earth's atmosphere give off thermal radiation. So you would have a deficit in the wavelengths that are absorbed by greenhouse gases, but you have a corresponding surplus in all the other wavelengths, so that the same amount of energy is given off at the top of the atmosphere. Global warming is not being caused by greenhouse gas emissions. It's not being caused by anything to do with greenhouse gases. What drove the temperatures down was volcanism. What's driving the temperatures back up is a lack of volcanism. Okay, and the only mechanism that might be powerful enough to combat that is evaporation, and we can increase the Earth's evaporation quite easily by putting water in the deserts and irrigating much of the Earth's deserts. So those are the main conclusions from the 3 videos. I hope you've enjoyed them, and I hope you'll check out the facts and dig into it and verify them for yourself, because when I did this study, I had no idea that these are the things that I was going to find. I was expecting to find an easy way to increase Mars's temperature by having a certain amount of carbon dioxide and a certain amount of atmosphere. And what I found was overwhelming evidence that global warming is not being caused by greenhouse gases of any kind. It's not being caused by carbon dioxide. It's not being caused by any other greenhouse gas. If the global warming that's happening is being caused by a lack of volcanic hyperactivity, and the Earth's temperature is not set by the amount of greenhouse gases. The Earth's temperature is being set by sunlight coming from the sun and pressure creates the surface temperature, and then it's modified by the cooling mechanisms, including evaporation. So I hope you've enjoyed these videos. Thanks for watching.